Now let's compare the graphs of y equals x to the 1, and y equals x to the 2, and y equals x to the 3, and y equals x to the 4, and so on. Things like that. See what happens when you keep raising the power. We're trying to figure out what to do beyond just degree 2. So we're looking right now at the moment at degree 9, now degree 10, back to degree 1, 2, 3, 4, 5, x to the 6, x to the 7, x to the 8th, x to the 9th, x to the 10th, x to the 1, x to the 2, x to the 3, x to the 4. And do you notice kind of a pattern? Do you notice something going on with every other? So they all have something in the first quadrant, okay? But you'll notice that every other, something's going on the left side, right? So either it's going upwards or going downwards. And I'd like to describe it the following way by saying that there's kind of a, let me pause this, like at n equals 2. There's a bounce effect here when n is 2, and when n is 4, it bounces. Just hits the x-axis and bounces right back. Same with n equals 6, just bounces. But when you have n is odd, like 3, it doesn't bounce, right? It's like goes through the x-axis. Same deal when n is equal to 5, it goes through. So what we ought to notice in y equals x to the n, if the exponent is even, then the graph bounces at the x-axis, and when the exponent is odd, the graph pierces through the x-axis. We can actually see that same behavior. Let's take a look at y equals quantity x minus 3 to the nth times x minus 5, and we'll change up the value of n. So by that I mean, like, let's try n is 1, and n is 2, and n is 3, and n is 4. So for instance, we'll look at x minus 3 quantity to the 4th times x minus 5. Here's what this looks like. Whoops, this does not look right. Let's try that. Let's just try. I'll fix the link later. Whoops. Let's do here x, what was it, x minus 3? I'm going to have to go back and look. Yeah, x minus 3 to the nth times x plus 5, or x minus 5, excuse me. Okay, so take a look right at 3, right here. So see for various values of n, how again we either have a bounce or a piercing through. Sorry about the wrong link there. So at x equals 3, we have a bounce if n is even, and a pierce through if n is odd. So there's actually certain language we'll use for the exponent that appears for x minus 3. So it's x minus 3 raised to the first, or x minus 3 raised to the second, and so on. So if it's x minus 3 raised to the first, we're going to say that 3 is a 0 of multiplicity 1. And here, for g of x equals x minus 3 raised to the second times x minus 5, we'll say that 3 is a 0 of multiplicity 2. And when you have x minus 3 raised to the 94th, we'll say that 3 is a 0 of multiplicity 94. We can also say that this function g, because the multiplicity is 2, another way to say the phrase multiplicity 2, we'll use this phrase double root, or double 0, at x equals 3. So here's some, based on what we had just seen with Desmos, here's some pictures of what multiplicity ought to look like. So if you have your function written in a factored form has a factor of x minus 6 quantity raised to the mth, where that exponent m is odd, then the picture will pierce through. It'll either look like this, piercing through the x-axis at 6, either this way, going up, or going down. If you have x minus 6 raised to an even power, then the picture is going to be a bounce right at 6, and it'll either look like this, bouncing right at the x-axis, or like that. So let's find a polynomial f of x of degree 4 that has zeros 2 and negative 1 and 5, with 5 having multiplicity 2, and we're also supposed to have f of 6 equals 3. So the function should be of the format f of x equals an unknown number a, we've used k before, now it's an a times quantity x minus 2 times quantity x plus 1 times quantity x minus 5 squared. So this has the right zeros, yeah? So 2 needs to be a 0, so that's why there's this x minus 2. Negative 1 has to be a 0, so that's why there's this x plus 1. 5 has to be a 0 or a root, so that's why there's an x minus 5, but it's of multiplicity 2, which is why the exponent is 2 here. So this has the right multiplicities, right? The right zeros with the right multiplicities. Now we need to find the stretch factor. That's where this information of f of 6 equals 3 is going to be helpful, right? we have that 6 comma 3 is a point on the graph. So if we plug in 6 for every x, we have f of 6 is equal to a times 6 minus 2 times 6 plus 1 times 6 minus 5 quantity squared. If we we also should take into account that f of 6 is equal to 3, so we can replace this f of 6 on the left side with a 3. And we'll have 3 equals, and simplify the right side to be a times 4 times 7 times 1 squared. In other words, if you divide both sides by 28, 3 over 28 is equal to a. And so that means our function back here, we had the format. Now we know what a is. So f of x is equal to 3/28 times quantity x minus 2 times quantity x plus 1 times quantity x minus 5 squared. Interactive question: why did we vertically stretch instead of vertically shift? What would go wrong if we vertically shift to get the graph to go through the point 6 comma 3?